Here are some examples on how to use the integral tables. And so the first one is this integral right here. So we have to see in the table, and the form looks something like this one right here. So that's in part 6, number 28. So we're going to go for that form. But notice that it has just x squared here, not 16x squared. So we have to factor out the 16. So we'll just take the integrand right here, factor out the 16, and write what's necessary back in the parentheses so it equals back out to 25 minus 16x squared, which is this right here. So then we're good to go there. So then we just continue on here. The square root of 16 comes out as 4. 25/16 we have to write as 5/4 squared, and we have to do that because over here you have the a squared, so you need it as a number squared. So now we rewrite, here's our original integral right here. Now we just rewrite the integrand with the 1/4 coming out here, 1/4, running with the a squared and the x squared square root. Then we have our rule here from the integral table. So we just finish it up by bringing the 1/4 down here like this, and then our answer is arc sine x over a plus, I always like to say c1, so that when I distribute in the 1/4 I just get the c, and so here's our answer. Okay, check it. Check number 1. As usual, put in the Wolfram alpha, the integral of the original problem there. Sure enough, it says it's 1/4 arc sine 4x over 5 plus a constant. That checks out. Of course, you can also check it out by taking your answer and take the derivative of it, which you could do in Wolfram alpha or by hand. Take the derivative, you'll have a 1/4. Derivative of arc sine of an angle is 1 over square root of 1 plus the angle squared times the derivative. Here's the derivative of the inside function, which is 4/5 x, is 4/5. That's the chain rule. Then square everything out, get to here. Then we realize that we have a mistake here. This should be a 4, not a 5 out there. So then this will be actually, that was a 1/5, because you have 4/5 multiplied by 1/4, which does indeed come out 1/5. So that was correct. Now we would square the 5 and move it in as multiplying here on that quantity. It would become 25 inside the radical, and then multiplying over and distributing, you would indeed get the original integrand. So that's another check. Another problem here is this one, integral of 1 over y squared plus 4y plus 5. The closest thing we can find to that will be this here, this one, but it doesn't quite look like that. I don't see x squared plus a squared on the bottom. I see this polynomial. So let's complete the square on that polynomial. Take the 5 off, write it last, create a number, and take it away. That will complete the square. So 1/2 of the 4 quantity squared, that's 2 squared is 4. Subtract the 4 so we're not changing the value of the polynomial, and we have the 5 added on. So this is the same as the original polynomial. But we now are able to complete the square on this part right here. Y plus 2 quantity squared, and 5 minus 4 is your 1. So we go back to the original integral right here. Now we know it can be rewritten this way. Y plus 2 squared plus 1 in the denominator. But that's not exactly what the form is either, because they don't have a plus 2 in there, they just have a x squared. So u will equal y plus 2. du is 1 dy, so du is dy. Change it over to u, doing a little substitution there, and you get this integral. I rewrote the 1 as 1 squared in order to make it look like the proper form. So I'm in the proper form now as far as my u's. So I realized that a is 1, because there's the 1 right there. That's the a. So a is 1. So I have 1 over 1 right here. Arctangent u, because I'm in u's, u over a is 1, plus a constant. So that's plugging back u, which was y plus 2. I have arctangent y plus 2 plus the constant. Checking in Wolfram alpha, we could check the original integral, or this time I'm just going to take the derivative of arctan x plus 2, and sure enough you get back to the integrand of the original, which is 1 over x plus 2 quantity squared plus 1. Of course it was with y, but really no difference there. Okay, now this last one. You're being trained by doing a lot of the problems that you can always break up multiplying factors to end up with what you want. So this is what I thought of doing. Let u be x squared so that du is 2x dx. Then I can rewrite this integrand as 2x x squared. That's your x cubed, but I have an extra 2, so I have to remove it as a multiplying factor. 2 times a half is 1. But see how I split apart? The x cubed is right here, and I have sine of x squared there. So now I'm going to substitute everything. 2x dx is the du, the x squared is the u, so sine of u, and this x squared right there was the u. So this is the integral I now have. Now I'm going to look through my integral table and realize that in part 3, number 15, I have an integral of a polynomial and a sine of ax. Now we could do this integral right here by parts, and that's really exactly what they did do to get the integral in the integral table, but let's just follow them for this one. So the a is 1 because it's a 1u. The polynomial is just the u. So going to our integral that we have, 1/2 u sine u, following the template, will be 1/2 on the outside, that's coming from here, and we should have negative 1 over a, so negative 1 over 1, p of x, that's the u, cosine 1u, that's here, cosine 1u, plus 1 over a, but a is 1 over 1, integral of the derivative of the p, the polynomial, which is in this case u, cosine of 1u. Now I'm not making a substitution here with x and u, I'm just following the form. This is just a form of what we're doing. This happens to be all in u's. Okay, so now then I simplify down, and I have my 1/2 negative u cosine u plus integral of the derivative of u is 1 cosine u, and when I come down to this step, first I did the integral, and that was sine u plus a constant. Then I distributed into 1/2 on everything, and it's here now. Now we distribute the 1/2 in, 1/2 c1 becomes c. Now we remember that u was x squared, so plug that back in and you get this. Let's check it. Integral of the original, let's put it in Wolfram alpha, and you do get the original, the same answer as they got, because 1/2, here's your negative 1/2 x squared cosine of x squared, check. 1/2 of sine x squared, check, and the constant.